Alright, one more video with this molecule. This will be the third video with this molecule. If you haven't watched the other two, go back and do that first. So in the previous video, we ascertained that there are 3 chiral centers in this molecule. So how many possible stereoisomers are there for the molecule? Well, as you know from class and other videos, the maximum number of stereoisomers, first, what is a stereoisomer? A stereoisomer is going to be a diastereomer or an enantiomer. Molecules that are connected exactly the same, so that in 2 dimensions you could lay them over, but aren't going to, so exactly the same in 2 dimensions, connected exactly the same, but are not superimposable. So maximum number of stereoisomers, 2 to the n plus n. N is equal to the number of chiral centers. M is equal to the number of isomerizable double bonds. And I think it's M, isomerizable double bonds, that sort of trips people up most often. Well, 3 chiral centers, that's easy enough. So 2 to the 3 equals 8. So if you only look at chiral centers, you would say 8. There are 8 possible chiral centers here, or possible stereoisomers. But what about the double bonds? We have a double bond there, and we have a double bond here. It's not carbon-carbon, but you have to consider it. And so, right, the nitrogen has lone pairs. And so, in fact, this nitrogen-nitrogen double bond can be cis or trans. Here it's trans. The 2 lone pairs are trans to one another. You could have an isomer where the 2 phenyl rings, the 2 benzene rings were on the same side, the 2 lone pairs are on the same side. That would be cis. So this could be cis. So M is at least 1. What about the double bond in the ring? And this is tricky, and you may have not gotten this. So if you answered 2 to the 3 equals 8, you're on your way. If you answered 2 to the 4 equals 16, you're correct. The answer is 2 to the 4. There's 1 isomerizable double bond, there's 3 chiral centers, so 2 raised to the power of 4, 16. What if you said, how many of you said 2 to the 5 is 32? If you said that, at this point in your development, this is a pretty acceptable answer because you identified this as a double bond. I'm now going to erase the molecule, so if you want to see anything about this, the answer again is, I'm going to put up the final answer. There are 16 possible stereoisomers for this molecule. All right. You can be done. If you understand it, you can be done. I'm going to erase the molecule and just look at the 6-membered ring and talk about why the 6-membered ring double bond is not isomerizable. All right. This is, if you look at it, a cis alkene, right? Both, it's trigonal planar. The hybridization of the carbons is sp2, so it's flat. If you look at this, the H's are on the same side of the double bond, the 2 carbons are on the same side of the double bond, so it's cis. Well, why can't it be trans? We'll try to do that then, okay? So if it's trans, there are the H's. Well, now the carbons have to be on opposite sides of the double bond. But it's a ring, remember? So we have 2 carbons left. So right now, let's number these. So 1, 2, 3, 4, 5, 6, just arbitrarily. 1, 2, 3, and then this will be 6. We've used up 4 of our carbons. We have to connect carbon 3 and carbon 6 using only carbons 4 and 5. And it works out that you can't do that. So if the normal bonding is there, so 3, 4, all right, we're now out of carbons. We've drawn all the carbons, and carbon 4 is a very long way away from carbon 5. So the ring actually constrains the rotation not even the rotation, the isomerization of that double bond. It's not actually possible to make a stable six-membered ring with a trans double bond. So sorry. All right, so double bonds in rings smaller than 8 aren't isomerizable. So that was not, you recall from the earlier molecule, rewind to see it, there's a six-membered ring that has a double bond, but that double bond is not isomerizable, so it can't be cis or trans, it can only be cis, and therefore it doesn't contribute to the number of possible stereoisomers. All right.